goal of this talk is to introduce an ensemble reduced density matrix function theory, which allows us to calculate excited state energies. And this will be the first half of the talk to just introduce to you this new method and also explain how it fits into existing literature. And then in the second part of the talk, we will discuss the consequence of this new 1-RDMFT, namely that by describing the domain of the function, we obtain a hierarchical generalization of Pauli's exclusion principle, and I will explain in more detail later what this means. So now to clarify the notation I'm using, here's first a short motivation. So the 1-RDM is, in my case, always denoted by small gamma, and that's simply obtained by tracing out n-1 particles of the n-particle operator capital gamma. We always normalize the 1-RDM to the total particle number here, because then its eigenvalues, they are simply given by the natural occupation numbers, and then alpha denote the corresponding natural orbitals. And it will be exactly those lambda alpha, which I will use later in the talk when we discuss the generalized Pauli exclusion principle. Okay. So now for 1-RDMFT, there are two important observations. So first of all, the part which we vary is the one particle Hamiltonian. So that's both kinetic energy and external potential. And the conjugate variable to the one particle Hamiltonian is the 1-RDM small gamma. What I mean by conjugate variable here is that if you want to calculate the expectation value of any one particle Hamiltonian, then the minimal quantity you need to know is exactly the one part reduced density operator small gamma. And as said previously, we discuss Hamiltonians with fixed interactions. So in quantum chemistry, that's usually a Coulomb interaction, but we could also apply to different fields like what are called quantum gases, etc. We have contact-like interactions, and there are many more examples. But what it means when we keep this interaction fixed is that we discuss Hamiltonians, so total Hamiltonians, which are parameterized by the one particle Hamiltonian small h. And now the idea in RDMFT is that you want to put a lot of effort into the second term involving the interaction, and then solve the ground state problem for this entire class of one particle Hamiltonians simultaneously. And this method was formulated in three different ways by Liebert, Levy, and Valone, as in this chronological order, but always have the same thing in common. We have some energy function, which consists of somehow the one particle energy, and the universal functional, which contains only the interaction, but no information about the one particle Hamiltonian. And then we just minimize this energy functional over all 1-RDMs to obtain the ground state energy E of H. Of course, the set you minimize over, it depends on the formalism of RDMFT, 1-RDMFT you use. So there are mainly two nice aspects, which are always valid. First of all, when we apply wave function-based method and we change the one particle Hamiltonian, we have to start our calculation from scratch. That's something we avoid here if we would know the universal functional. But at the same time, we don't trivialize the problem, because usually the really hard part is to obtain a sufficient approximation for the universal functional. And in contrast to DFT, of course, we have more freedom to vary, but this also means we have less to approximate in the functional because the kinetic energy is not kept fixed. And also 1-RDMFT explicitly allows for fraction occupation numbers through the eigenvalues of the 1-RDM, and by just looking at them, we can already guess how strongly or weakly interacting the system is. It's something which you cannot tell from the particle density alone. Okay, so for here, up to this point, everything is just ground state 1-RDMFT. So I said in the beginning that I want to talk about excited states. So let us compare the literature or the existing literature for DFT and 1-RDMFT. For ground states, of course, we have in principle a formalism for both, with advantages and disadvantages on both sides. Now for excited states, in the case of DFT, there are basically two different approaches. The first one is a time-dependent DFT, and the second one is an ensemble DFT. For 1-RDMFT, there's also people used time-dependent 1-RDMFT. However, we don't have such a mathematical or conceptual foundation as in time-dependent DFT through the one coarse theory because one cannot simply generalize it to non-local potentials. And an Ensemble 1 RDMFT to calculate excited state energies was missing in the literature. And that's exactly what I want to introduce today in this class. So here's a short outline of the talk. We will start with the foundations of excited state 1 RDMFT. This will define the function, also the functionless domain. So in the second part, we will then obtain an efficient description of the domain of F. And then in the last part, I want to discuss consequence of this principal constraints. So to start with, the foundation of one RDMFT, well, as in ground state RDMFT, it consists of two parts. We have to combine a variational principle, similar to the Liebert variational principle, but adapted for excited state, together with a constraint search. So the formalism should be very familiar to all of us already. And we will start with the variational principle. So let me briefly recap something we all know. That's for ground state 1 RDMFT, we would simply use the Liebert variational principle, which we know from quantum mechanics course. And here we obtain the ground state energy 1 by simply minimizing over all states psi. And you can also visualize it in the way that all the weight here shown in red sits on the lowest energy level E1, which would be the ground state energy. And now we can ask, well, what happens if we reduce some of the weight on this lowest energy level and place it on the second lowest one, so on E2, which would be the first excited state energy. One can do it, and then you obtain a slightly modified variational principle. So instead of minimizing over all pure states, we then minimize over all density operators with spectrum given by W1 and W2. Here we have again just the expectation value of the energy, and what you obtain is the weighted sum of the ground state energy and the first excited state energy. So if you would choose, for example, W1 equal to W2 equal to 1/2, this would just give you an equal mixture of ground state and excited state energies, as you would also expect. Of course, from here you can already guess how this generalizes to larger numbers of non-zero weights. So we just do the same as previously. We now minimize over all density operators in the set En of W, but this set is just characterized by the spectral constraint, namely that when I order the spectrum of the density operator gamma decreasingly, then this should be equal to the weight vector. So that's the same we had on the previous slide, but no for arbitrary number of weights. And what we then obtain from this minimization of the energy is just the weighted sum of the lowest eigenenergies E chain. So there are also again two comments in order. So first of all, in practice, you will only choose a finite number of non-zero weights, and this then also determines, of course, which energies, excited state energies, you can extract from your functional theory. And then we just take this energy E of W, we just copy this line here, and we go to the variation to the constraint search, where we insert this variational principle. So that's it's just the same as the Levy-Leap constraint search, just with this adapted Grok variational principle for excited states. We minimize over all the density operators in the set En of W. Then here I just wrote my Hamiltonian as H plus W. We can split the trace at the plus sign such that the first term reduces to the trace over only one particle. And then for the second term involving the interaction, we also split the minimization such that we first minimize over density operators mapping to a given one RDM, and then afterwards we minimize this entire expression over all one RDMs. And then as in ground state RDMFT, we can identify the second term as our universal functional F. Now, of course, since the domain or the set En of W is weight dependent, in general also the functional will have an explicit weight dependence. And in particular, this means that for each weight vector, we have a different functional theory. But what we achieved here is we were able to define this functional F, which lives on some set En of W, just maps to the real numbers. And now the domain of F, this blue set here, is simply obtained by tracing out n-1 particles of all particles in or density operators in the set En of W. In channel, both of them, the big set on the n particle level and the set E1n of W on the 1 particle level will be not convex. You can immediately see this if you would add 2 density operators in the set En of W with fixed decreasing ordered spectrum given by the wave vector. This, if you add them, you usually have a different spectrum. But the big problem here where I say that describing the set is extremely complicated is actually another one. So we see that here we contain ground state RDMFT as a special case. So if we would just choose the wave vector to be 1, 0, 0, 0, then we would recover Levy's 1 RDMFT, and then the set here, the blue one, would be described by the generalized Pauli constraints, which are only known for artificially small systems. So when we here have arbitrary spectra, then this will be, solving this problem will be even more complicated in general. So how to circumvent this? For this, we have to apply, or we had to apply an exact convex relaxation. This consists basically of 2 parts. So on the level of the functional domain, this means to replace this horrible blue set by its convex hull. And then on the level of the functional, we will replace this possibly non-convex blue functional, which lives on the blue domain, by its lower convex envelope. And this, of course, from a computational point of view, also has the advantage that we won't get stuck in a local minima anymore. Also here, we see that for W, the wave vector equal to 1, 0, 0, so ground state 1 RDMFT, this exact convex relaxation would again lead to Valone's formalism. And here, exact, maybe that should, something I should mention, just means that by applying this convex relaxation, we don't change the outcome of the energy minimization. And this is then exactly also what allows us to turn this excited state 1 RDMFT into a feasible method, because it actually allows us to obtain an efficient description of the functionalist domain, so of the convex hull here. And that's, of course, what I have to do next. So let me briefly illustrate the most important concepts. So the first one is a duality principle for compact convex sets. This basically means that I can either characterize my set for all the points in the set, so basically through the indicator function, or I can use the intersection of all supporting hyperplanes would lead to the support function. And now what does this mean in our more physical terms? Basically, we have to minimize over linear functionals, but they are just given by the inner product between the 1 particle Hamiltonian and the 1 RDM. So this defines as some geometry on the space of 1 particle density operators. And we just have for fixed h, here we have this defines a hyperplane of fixed value. And then we just shift this hyperplane in the direction of -h until we touch the boundary of our set. And now here, this is illustrated for just one direction. And if we would do it for all possible directions, so for all possible 1 particle Hamiltonians, we would get all the extremal points, which is illustrated on the right side. But this is not sufficient. The second important ingredient is a unitary invariance. And this just means when I pick a 1 RDM in set, in this convex set E1n bar of W, I apply a 1 particle unitary from left and right, then the new 1 RDM will be again in the set. And the reason for this is simply that on the n particle level, En of W is just constrained by the spectral constraint that when I order the spectrum decreasingly, this should be equal to the wave vector. And of course, by unitary transformations, we don't change the spectrum. That's all in here. But what this means is that we can reduce to describing only the spectral polytope sigma of W, which is just a set of all possible spectra. And that's sufficient. So when we combine those 2 ingredients, what we achieved is the following. So we had in the beginning this mathematical problem of minimizing linear functionals. And we were able to map this to the physical problem of describing the excitation spectrum of non-interacting fermions. And that's, of course, something we as like physicists or chemists have some intuition how those excitation spectra should look like. And this is then what allowed us to obtain first the vertex representation of those spectropolytopes, and then afterwards the hyperplanar representation, which is actually the important one because it allows you to efficiently test the membership problem during the optimization process of the energy functional. Okay, here I don't want to look further into the technical details, and I would rather like to discuss the results. So we were then able to obtain this hyperplane representation of the spectropolytope. And here I first illustrate this on a very qualitative level. So R denotes the number of non-zero weights. So I equal 1 just means basically ground state item of T, we have 1 non-zero weight. And for I equal 2, we have 2 non-zero weights and so on. So if we go from left to right, for I equal 1, always sits on the ground state energy level. You can think about this square as like here having one occupation number lambda I and then lambda j. And we know from Valone's RDMFT, it would be just constrained by the Pauli exclusion principle, which basically gives you this entire Pauli hypercube. Now, if we go to R equal 2 and we have a non-zero weight on the second lowest energy level, then we get an additional constraint, which restricts this set further. If we go to R equal 3, we have again the same constraint here, but we also have this additional constraint here. And as a result, the volume of the polytopes or size of those polytopes becomes smaller and smaller. The more non-zero weights we include into our formalism. Now, to make this more precise, I would also like to show the inequalities. Of course, how exactly they look is not that important, not important to remember. So for I equal 1, we just have the Pauli exclusion principle, as we also see from the picture. For I equal 2, the first inequality is still valid, plus we have one additional one. Pauli would tell us that this should be, if we sum the n largest occupation numbers, this should be lower or equal n, but since W1 is positive, this bound will be more restrictive. Now for I equal 3, we have again those two inequalities, which we can also see from the picture, like here, and then this one we already have from I equal 2, plus one additional one. And this pattern then continues for larger and larger numbers of non-zero weights. So we always have the previous inequalities plus a finite number of new ones. And this is then what we refer to as a hierarchy of exclusion principle constraints. So, well, what does this now mean? In principle, we have also in ground state RDMFT one unfeasible version of describing the functionalist domain and one feasible one. So let us start with the unfeasible picture. So there was an important result by Klatschko regarding the former solution for the generalized Pauli constraints, but really to evaluate them or to obtain them in practice is extremely complicated. And therefore we don't want to apply one RDMFT on such a domain or such a setting. Now, if we include also mixed states, the problem will be even more complicated. And there was also some work done by Klatschko. Now, on the feasible side, we know that what saved ground state one RDMFT more or less is the result by Coleman, who proved that the ensemble and representable one RDMs are just restricted by the simple Pauli exclusion principle. This has the big advantage that it always takes the same form, independent of the particle number and the dimension of the one particle Hilbert space, in striking contrast to Klatschko's generalized Pauli constraints, which depend very strongly on N and D. And now what we did here in collaboration with Jean-Philippe and Federico, whom you met on Monday, is we actually solved the relaxed problem for mixed states. So we also obtain constraints which are effectively independent of the particle number and the dimension of the one particle Hilbert space. So this is in striking contrast to the GPCs, but it's again an analogy to the Pauli exclusion principle. And therefore we can conclude that these constraints are really a generalization of the Pauli exclusion principle for mixed states. And well, how did we achieve this? Maybe it's important to stress this again. So of course, there was, in context of the one-body quantum marginal problem, the breakthrough result by Klatschko. So he had both on the n particle and the one particle level, these convex, non-convex sets, and describing them is extremely complicated. Where what we do is instead, we look at the convex problem on both the n particle and the one particle level, and we can obtain in both cases a very efficient description. And in particular, we don't lose like physical relevance because we don't change the outcome of the energy minimization. So that's good for us because it means that we can, at least on a conceptual level, provide a practical 1R DMFT for excited states. So as a summary, we started with the foundations of excited state 1R DMFT. Here we combine the variational principle suitable for excited states together with the constraint search. The key ingredient to obtain a practically feasible 1R DMFT for excited states was to apply an exact convex relaxation. This also may emphasize again that what Valone's 1R DMFT is exactly the same, and we just contain Ensemble ground state 1R DMFT as a special case. And then in the last part of the talk, we discussed new hierarchy of the generalized exclusion principle constraints, which arose from describing the domain of our functional. Of course, maybe a short outlook, you can do exactly the same for bosons. Not much will change, except we have different combinatorics. So when we describe the domain, when we obtain the hyperplane representation and all those inequalities, of course, this will change. So you have to execute it again, but that's doable. And now two important or interesting open questions are the following ones. First of all, maybe not everyone is interested in functional theory. So it would be interesting to discuss possible applications of those exclusion principle constraints beyond functional theory, as Pauli exclusion principle is very important for almost all parts of quantum physics. And then the second really big problem or open task in the context of 1R DMFT is to really develop functionals and then also test the practicability of the method. And that's both of them are still work in progress. Yes, so with this, let me thank you very much for your attention.